Alright, well, welcome back. We are going to continue our discussion of Chapter 10. So we talked first about energy, work, and power, and now we're going to relate that to simple machines. And you're going to want to be kind of thinking about these when we get to the Rube-Goldberg device, because part of the requirements are to include one of each type of simple machine in your design. So let's talk about what a machine is. A machine eases the load by changing either the magnitude or the direction of the force to match the force to the capability of the machine or the person. So usually we're changing it so we can apply a small force and the machine will produce a larger force, but we could also change the direction of that force. So push down and then something else moves up. So those are some benefits to machines. And let's talk about some variables that will help us calculate the benefit of machines. So the work that you do is called input work, and this is abbreviated as W sub I. The work that the machine does is considered to be output work, and we're going to abbreviate that with W sub O. And so we're going to look at the difference between how much work you put in and the output work of the machine. Output work can never be greater than input work. Remember, machines change the direction or magnitude of force. Okay, so when we talk about work, force is a part of that. But output work can never be greater than input work. The machine aids in the transfer of energy. So let's talk about mechanical advantage. Well, we have what's called an effort force, which is the force exerted by the person on the machine. So if you're pulling on a pulley or pushing down on a lever or anything like that. The resistance force is the force exerted by the machine, and we're going to put that symbol as F sub R. So to find the mechanical advantage, which is the ratio of the resistance force to the effort force, we would take the force exerted by the machine divided by the force exerted by you, and that's what's called the mechanical advantage. Either increases the force applied or changes the direction of the effort force is what a machine does. So remember, we're looking at the force and either changing the magnitude or the direction. We can also have what's called ideal mechanical advantage. Okay, and we can write this in terms of work. So a machine, remember, can increase force, but not energy. Well, an ideal machine transfers all the energy, right, because it's an ideal situation. Well, so this would mean that work output is equal to work input, or force of resistance times the distance of resistance, resistance being the machine, is equal to the force exerted times distance exerted, exerted being like you or what you do. We can rearrange this to write it as the ratio of F of R over F of E, which remember was our mechanical advantage, divided by the distance exerted divided by the distance of resistance. This is equal to the ideal mechanical advantage. And so it's the displacement of the effort force divided by the displacement of the load, which is the resistance, which we're going to consider as the machine. So let's talk about the difference between ideal and actual. So for ideal mechanical advantage, this measures the distance of the displacement, whereas actual measures the forces that are exerted between you and the machine. And we can relate this to what's called efficiency. Well, not all input work is available as output work in an ideal world. Okay, we said that an ideal machine input was equal to output, but in the real world it's very difficult to have that. And so we have what's called efficiency, which we're going to abbreviate with a small e. And this is the ratio of output work to input work. So we've got output work divided by input, and then we multiply by 100 to get a percent. So like we said, an ideal machine has an efficiency of 1 or 100% because all the input work equals the output work. But that's very rare. Real machines have an efficiency of less than 1 or less than 100%. And I think a vehicle is in the 30 or 40% range, so not very efficient at all, although that's changing. Okay, in terms of mechanical advantage, efficiency is equal to mechanical advantage divided by ideal mechanical advantage times 100. So same idea. Alright, well let's relate this to a more practical situation, which would be compound machines. Very rarely do we have just one simple machine. We usually put them all together, and this is what's called a compound machine. So for our 6 simple machines that we're going to look at, and that need to be incorporated into your Rube-Goldberg device, they're the lever, the pulley, the wheel and axle, the inclined plane, the wedge, and the screw. Compound machines are a combination of 2 or more of these simple machines. So let's look at some pictures. Okay, so here we have a lever, and here is your pivot point or fulcrum. Effort is in one spot, load is in the other. You can see that the direction is the same, and so here we're changing the magnitude. Okay, here's a wheel and axle. Effort is here to go around the wheel, and then it turns and pulls and changes the load. Here we have a pulley. Effort force in this direction. Load is pushing down in that direction. Okay, here we have an inclined plane. You apply an effort this way. The load is pushing down this direction. Wedge, we've got the load towards the wedge and the effort kind of down between to like split a log or something like that. And then we also have the screw, and this is definitely an example of a change in direction. So our effort force is upwards and our load is down. Okay, well remember we said the ideal mechanical advantage is the ratio of distances moved. So for some machines like the lever and the wheel and axle, where on the lever we talked about the fulcrum point, the ratio of distance is the ratio between the place where the force is applied and then that fulcrum or the pivot point. So the mechanical advantage of a compound machine then is the product of the mechanical advantages of all the simple machines that make up the compound machine. And so you'd find each of them individually and multiply them together. Okay, so let's kind of review. Machines make things easier by changing either the amount or the direction of the force. To find the mechanical advantage, we take the force of the resistance or the machine divided by the force exerted, which would be your force that you exerted. Ideal mechanical advantage is the displacement exerted divided by the displacement of resistance. And we can also put these into an efficiency equation by either taking the output work divided by the input work, or the mechanical advantage divided by the ideal mechanical advantage, and multiplying by 100 to get a percent. We've got 6 simple machines: the lever, wheel and axle, screw, inclined plane, pulley, and wedge. And if we put two or more together, we make a compound machine. And to find the mechanical advantage of the compound machine, it's the product of all the mechanical advantages of the simple machines. Okay, these are the practice problems that we're going to do together in class, and then here's the individual practice along with the answers. Have a good day.